Morning, my name is Ramjan Dev and Pitong, and I will be presenting my completion activity for a DHDL. So, here's the exact problem statement. The function was given as a product of max terms. My goal is to convert that to a minimized SOP or sum of products and implement the results in three modeling styles, both for Verilog and VHDL. As we can see, the function has five variables: a, b, c, d, and e, which means there are 2 raised to the 5 or 32 possible input combinations. The given expression is in terms of max terms, so where each listed index represents a conditions where the output is 0. To convert this into min terms, we can construct a truth table and assign zeros to the specified max terms indices. So, and all the remaining combinations where the output is 1 represent our minterms. Alternatively, we can obtain the same results by taking the complement of the given max term list, that is by subtracting the max term indices from the full set of 0 to 31. This gives us the 16 minterms where f is equals to 1, which we then plot on our K-map for simplification. So for a 5 variable function, I use two 4 variable k-maps. One for a is equals to 0 and one for a is equals to 1. So each cell corresponds to a unique B, C, D, and E combinations. So we will be grouping the adjacent ones from to form implicants using wraparound adjacency and group size of size power of 2. Here's the annotated K-map. So I explain each colored, no, colored group and how it yields a product term. Starts with the A is equals to 0 plane on the left side. So the purple pair at the top left covers the midterm 0 and 1 and yields not A, not B, not C, and not D. Because A, B, C, and D are fixed while your E varies. The green group covers the midterms 5 and 7 and the adjacent ones and yields not A, not B, C, and E. So the magenta group yields B, C, and not D. The orange yields B, not C, D, and E. On the A is equals to 1 plane, on the right plane, the tall green column of 4 cells gives A, not D, and E, while the red and pink pair gives B or not B, C, D, and not E. The blue pair yields A, B, not C, and D, and each group reduces the variables. Collecting the implicants from both A-planes yields the seven-term minimized SOP. It fully recovers the min terms originally found and is minimal as seen by the maximal groupings on the map. Next, we implement the function. So each modeling style targets the same logic but has different uses. The data flow, compact Boolean assignments, the behavioral, procedural for clarity, while your structural is the explicit gate instantation. We then create test benches to verify the behavior and record waveforms for visual confirmation. First, for the modeling concurrent functionality in Verilog, no, this code implements the simplified Boolean function using data flow modeling. It has a 5 input variables A, B, C, D, and E, and one output, the F. And the assign statement defines F as a continuous combination of 7 product terms or min terms using the logic operators NAT and end. And for the four, we will be using the design. So each min term represents a conditions where the output f is 1 and all terms are combined to form the sum of product. This design is purely combinational, meaning your f depends only on the current input values, making it clear and efficient to describe the logic behavior in the Verilog. And if you click on the link provided here, will be redirected on the EDA Playground. Now, for the right, we have our code, and for the left is our test bench. Now, before we run, now please click on the Open EP wave to generate our wave. Now, if you click on run, we'll run our code, and it will generate our waveform. Now, for example, for the not A, B, not C, not D, not E, or the 0, 0, 0, 0, 0, now we are generating an output of 1 for the 0, 0, 0, 0, 1, or on our truth table it is the 1. Now we are generating also an output of 1, and it checks on our record. So here, no, it has also generated our truth table 1, 1, 0, 0, just like on our waveform. So next, let's proceed for the structural design and the hierarchy using Verilog. So this Verilog code, as you can see in the PowerPoint, no, is used to implement the simplified Boolean function. And instead of using a single expression, it builds the circuit using logic gates like NOT, and OR. So each NOT gate generates the inverted signals NA to NE, and each AND gate T1 or to T7 represents one product term from the simplified SOP expression. So all these terms are combined using an OR gate to produce the final output F, and this approach closely mimics how the logic circuits would be built using actual hardware components. And for the structural design and hierarchy using Verilog, no, this is the simulation on the EDA Playground. Again, if you click on the link, now it will be redirected here. So for on the right, we have the design given our code, and for the left is our test bench. Now if we click on run again, it will generate the same output and waveform. So just we get signals, append all selected, and here as you can see on the code, no, on the A is equal to 0, B is equal to 0, C is equal to 0, and D is equal to 0, and E is equal to 0, we are generating again an output of 1. Same with the next. And for the 2, no, if we check on here, no, we have 0, the output is 1. On the 1, we have the output of 1 also. And for the 2, given on our max terms, we have an output of 0. So next, for the behavioral modeling using Verilog, this modeling is describe the logic function in a high level and human readable way. The module has 5 inputs variables, again A, B, C, D, and E, and one output F, declared as a reg type because it is assigned inside an always block. The always at asterisk block ensures that F is updated automatically whenever any input changes, making it combinational logic. So inside the block, the Boolean expression is written using logical operators and to define the conditions when F becomes 1. Each line represents a product term, and all are combined using OR operations to form the sum of products, or SOP. So this style focuses on describing the behavior of the circuit rather than its structural, making it easier to read and modify for simulations or testing. So next, no, in for the behavioral modeling using Verilog, if you click on this link, now we will be redirected again here on our EDA Playground. Just log in and to simulate our code. Again, on the right side, the design.sv file or our code, and on the left side is our test bench. If we click on run again, now it will generate the same output. For the waveform, we will just get signals and append selected. Now, again, on the 0, we have output of 1, 1, we have an output of 1 also, and for the 2, we have an output of 0. So for to check, on here, 0, 1, 2, 3, 4, 5, we have also an output of 1. So to check on this truth table, 0, 1, 2, 3, 4, 5, we have also an output of 1. So next, no, for the modeling concurrent functionality and VHDL, this code uses data flow modeling to implement the simplified Boolean function. So the entity has 5 inputs again, uh, A, B, C, D, and E, and one output F. The architecture uses concurrent signals assignments, so your F updates automatically when any input changes. So logical operators not and or are used to form the sum of the products expressions, where each term represents a condition that makes your F is equals to 1. So this style clearly describes the data flow of the combinational logic without focusing on the physical structure. Next, for the VHDL codes, no, for the modeling concurrent functionality, no, this is the link. So if we click again on this link for the modeling concurrent functionality in VHDL, we will be redirected here. So we will just copy our code. No, in this right side, we have the design.vhd. On the left side, the test bench. No, I'm using simulator tool as for Aldec Riviera Pro for the simulator tool, and just click on open EP wave, and to click to run, no, we will just click the run button here, and then it will running our code. It will generate also our EP wave, no? Just appending all of these signal names append selected, and again we are generating the same waveform. So to check for the truth table, here on the logs now, on iteration 00000, we have an output of 1, and for the 00001, we have also an output of 1. To check on the wave, 000 output 1, and for the 00001, we have an output of 1. Next, for the structural design and hierarchy, no, in VHDL, no, this code uses structural modeling to represent the circuit using logic gates. So the entity has 5 inputs again and 1 output. The internal signals NA to NE and T1 to T7 represents the outputs of the NAND, or represents the output of the NAT and AND gates, which generate the product terms of the simplified SOP expression. These terms are then combined using the OR operators to produce the final output, showing the gate level structure of the logic circuit. Next is for the structural design and the hierarchy using VHDL simulation. On the side, we have our code, and again, in the left side is our test bench. I'm using again the ALDEC for the simulators. If we click on run, it will give us our signals, the waveform, and yeah, we are generating again the same output waveform. Meaning we have a correct code. Just like here, on the truth table, we have also an output of 1, 1, and 0 for the first 3 numbers. Next and last, for the behavioral modeling using VHDL, this code uses behavioral modeling to describe the logic function. It has a 5 inputs again and 1 output F. Inside a process block, the output F is set to 1 when any of the specified product terms are true and 0 otherwise. And the if-else statement represents the sum of product or SOP expressions, and the process updates automatically whenever any input changes. So this style focuses on describing the behavioral of the circuit rather than its structure. So next and last is for the behavioral modeling on VHDL. Again, on the right is our code, and on the left is our test bench. Now, if you click on run, it will run our code and it will generate our waveform. So here, on the 8, 0, 1, 2, 3, 4, 5, 6, 7, 8, it must generate an output of 0. So to check our truth table, 0, 1, 2, 3, 4, 5, 6, 7, 8, no? Which b is equals to 1, we are generating an output of f is equals to 0. That checks our waveform.